Hey guys, my name is Will Buchanan, and this is my lab 3 over the magnetic field of a bar magnet. So a quick introduction, the purpose of this lab is to visualize and better understand how the distance relates to the strength of a magnetic field. Like when you get closer to a magnet, how much stronger or weaker does that field get? And the lab first involves an experiment where we use our phones, which actually have a magnometer inside them, and we use them to determine at what distances a certain magnet produces a specific strength. Then in the lab, we use GlowScript in order to create a computational model of this interaction. So some key concepts to understand are the Biot-Savart law, the magnetic field of dipoles, and superposition. The Biot-Savart law will help us calculate the magnitude or the strength of the magnetic field of the magnet we can find by using the data in our experiment. So in the experiment, the system I said was the magnetometer. I was thinking it could be the bar magnet, but since the magnetometer was always at the center of the experiment and it was what was getting acted on, I chose that to be the system. And for the surroundings, we have the bar magnet, like my hands holding the bar magnet, any nearby devices that may have been producing a field, and pretty much everything else. And a basic outline is you determine the true magnetic north by finding what direction you can turn your phone to make the magnetometer X value produces 0. And then you can determine the location of the magnetometer within the device by moving the device perpendicular to the magnet and finding where the X value maxes out, and then rotating your device and doing the same thing in the Y value to get the exact spot in your phone where that detector exists. Then you measure the horizontal distances where the magnet produces a net field of 20T, 70T, 120, 170, and 220. And then the next step is measuring where the magnetic field is 100, and then moving the device up in the Y direction the same distance to recording respective field values. So this is a quick preview of what things look like. This is the setup used to determine where the magnetometer is. This was determining the distance, at which distance, what strengths are produced. And this was part 3 of moving the magnetometer up the same distance to determine distance D. And here we see my data, and we see that as you move closer to as the magnet moved closer to the magnetometer, the strength increased greatly. And we see the value of the charges as well as the radii right here. And then these are all the averages of the produced by the magnet. And one thing to point out is that we had to correct our Y value data for the strength of the magnetic field produced by the Earth. And moving on to the code, this is just the magnetic moment I found using the Biot-Savart law and my measurements from the graph. And then down here, this is the function that will model the magnetic field. And here we had to set up our different observation points along the different axes. And then here we had to write out what was going on at each observation point and make sure that the arrows look good in our visualization. And then this was pretty much part 3 of the experiment. Here we see our perpendicular distance, and to find the length of D, we just use Pythagorean's theorem. And down here, we were just printing out our values. And this was produced from my code. We see the perpendicular forces here in the cyan. We see the magnitude of B at 45 degrees printed down here, which is visualized up here. And to compare our results, it was 5.36 to the -5th versus 1.4 to the -5th. And these aren't exact, but they're within the same, they're close enough. And discussion, when the magnetometer is far away, it measures a near zero magnetic field. Yes, I found that to be true. As it moved closer to the magnet, the magnetic field in the X value did not decrease. It actually increased a lot. And the position of the magnetometer has no effect on the measured X component of the magnetic field. No, the position matters a lot. It was very important to determine where in the phone the magnetometer was. And as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. Yes, this was a big part of the lab, and the data shows that pretty clearly. And what if you hadn't oriented your device for the Earth's magnetic north? The answer is the results would not have been accurate. The Earth's magnetic field would skew the results in all directions, and the results would become inaccurate and would be very hard to adjust for. And what if you stuck 2 magnets together end to end and ran the experiment again? How would you expect your measurements to differ? I would expect that it would pretty much just double, because there'd still be a positive and negative end if you think about 2 magnets stuck together. And I think their fields would just stack on top of each other. That's what I picture happening. I don't know if there'd be anything weird going on, but I'll stick with my answer that they will double. And some points of improvement would be to use an actual bar magnet. I sort of cheated and used a magnet off my fridge, which probably wasn't as good, but it did still have a north and south side, which was important. And I should have measured in meters from the beginning instead of using my ruler, which only had inches, and then converting those units. I should have repeated the experiment in multiple locations to account for any magnetic fields from external devices that could have been affecting it. And I could have used multiple magnetometer apps or even devices and averaged those for a more accurate result. That's all I have. Thanks for watching.